Hello, welcome to the Bakwas channel for self-paced tutorials on robotics. This presentation is an introduction to AprilTag technology for First Tech Challenge projects during the center stage season. Professor Edwin Olson introduced AprilTag at the University of Michigan. The AprilTag design permits robust detection and classification of the images. This feature provides a high degree of accuracy in determining the location of the AprilTag itself. AprilTag images are rendered as monochrome square patterns whose interior is darker than the exterior regions. This arrangement permits camera relative detection of an AprilTag with respect to 3D coordinate location and orientation. AprilTag technology has two major components: the tag detector and the coding system. For FTC applications, we will limit ourselves to the detection of the tag. The FTC SDK provides the API for very low false negative results. Unlike QR and barcodes, this technology permits more than one AprilTag to be present in an image. FTC teams that used AprilTag for signal sleeve detection last season, PowerPlay, can attest to the fact the variations in ambient lighting and distance from the camera did not handicap the accurate and consistent detection of the images. An AprilTag has two-dimensional reference markers for points of references. These markers are commonly referred as fiducials that are used for precise measurements related to position and orientation of the image captured by the camera. There are two generations of AprilTag families: AprilTag 2 and AprilTag 3. Each generation supports several different families of tags. The family nomenclature can be decomposed into two numbers. The first number before the H is the number of bits, and the second number after the H is the Hamming distance. More bits means more pixels are used for encoding. Conversely, lower bit tags can be detected at smaller image sizes. Larger Hamming distance means better error handling of reading errors. FTC uses AprilTag 2 generation. The recommended family is 36H11, which has 587 unique tag identifiers. The small amount of data computed from an image of an AprilTag makes the technology very efficient for robotics applications. The calculations provide estimates from the center of the camera lens to the center of the AprilTags in the image with respect to x, y, and z axial distances and the roll, pitch, and yaw, which essentially yields a 6 degree of freedom vector. The accuracy of the results is predicated by the calibration settings of the camera lens. FTC has published calibration coefficients for Logitech and Microsoft webcams. The supporting SDK has references to calibration techniques applicable to other cameras. If the webcam calibration has not been published by FTC, then it is very important to determine the coefficients with low error estimates. One of the advantages of AprilTag is the ability to leverage more than one tag in the same image. When using QR or barcodes, only one code in the image can be processed. The AprilTag processor will return the results of all tags detected in the image. The Opmode should have a strategy to select a pose when more than one estimate is returned by the detector. Example of selection picks are game strategy, same as the last iteration, or height, Z translation or elevation of tag within set tolerances. Truly speaking, a moving robot is not mandatory for these tests initially, but then it serves as the foundation to refine the tests incrementally to achieve FTC game objectives. The Driver Hub app must be at version 8.2 or later. The Control Hub app will be upgraded to 8.2 or later when running an Opmode from Android Studio. Onboard Java and Blocks users will have to sideload the app using the steps documented at the FTC SDK site. The camera connected to the Control Hub must have been calibrated previously. As mentioned in a previous slide, Logitech and Microsoft webcams have been calibrated by FTC, but other webcams will require independent calibration. While one can detect the identifier of an AprilTag, the pose estimates will be inaccurate if the calibration coefficients used by the AprilTag processor are not those for the webcam in use. FTC has chosen the AprilTag family 36H11 for the center stage season. It is a very popular choice since it has a vast range of unique identifiers and the detection accuracy is very good with very low false negatives. This AprilTag family uses 36 bits for encoding with 11 bits for Hamming correction. It has a low false positive rate which accounts for its popularity, especially when motion is present. There is a simple empirical formula to estimate the farthest distance at which this family of tags at a particular printed size can be detected with known camera lens properties such as focal length and resolution. Presently, FTC has specified two printed dimensions for the chosen AprilTag images from the family 36H11 for the center stage season. For some tags, the dimensions are 4 inches by 4 inches, while for others it is 6 inches by 6 inches. It must be noted that the printed tags must have a white border as shown on the slide. Thus, for a 4 by 4 tag, the effective dimension is 5 inches by 5 inches. Similarly, the border for the 6 inches by 6 inches tags, the effective border is slightly more than the 7 inches by 7 inches. In addition to the identifier, the tags have been assigned a name, perhaps for easier reference. Bose estimates have 6 degrees of freedom: 3 from translations, that is, linear movements in x, y, and z axes; 3 from rotations, that is, rotations of the axes stated as pitch, roll, and yaw. The world coordinate axes for AprilTag are aligned to the IMU coordinate system for the robot. The new drivers for the IMU in the control hub now permit any orientation to mount the control hub as long as the declarations reflect the orientation. The 3 types of pose data returned to the Opmode are distances, rotations, and range, bearing, and elevation. The distance data are reported for axial translations in x, y, and z axes. The rotations are pitch, roll, and yaw for the same coordinate axes as the field. These data permit the basic calculation of range, bearing, and elevation, which are also returned to the Opmode by the AprilTag processor functions. The distance values are reported in the x, y, and z axes with respect to the camera lens. As shown in the slide, the x and y are easily understood from a top view of the 3D axes of the camera lens. The z-axis, being orthogonal to the other axes, is perpendicular to project planes illustrated in the slide. For FTC purposes, the z-distance may be used for different purposes based on game requirements, if any. The pitch, roll, and yaw angles between the local coordinate axes of the camera lens and the target AprilTag is used for travel movements. While FTC use generally does not require pitch and roll in any significant way, the yaw is an important value for turn movements of the robot. Once again, it is important to note that the application of the right-hand rule for the axes. The thumb points along the positive axis and the fingers curl in the direction of positive rotation. For practical purposes, the yaw values from the AprilTag target and the IMU are applied to coordinate the precision turns for the robot. Since the AprilTags will be stationary, nominal assumption until Game Design Committee releases Game Manual 2, the turning will be performed by the robot where the IMU resides. A good combined algorithm will probably rely on a control algorithm for the turn using IMU data readings and using AprilTag results, if applicable, as an augmented filter. Once the axial distances and 3D local axes rotations are known, range, bearing, and elevation data are easily estimated by the AprilTag library routines in the SDK. These data may be useful in game situations where delivery can be launched by the robot. The tests in this tutorial have a narrow focus limited to detecting the AprilTags. The data returned from the detections are Bose estimates. However, in order to ramp up the learning curve, it is important to ensure that the detection is robust and works under varying field conditions. Having confidence in the Bose estimates will lead to improved calculations for the field location of the robot and its movement towards desired targets. These latter objectives will be explored in future tutorials. The 4 tests presented in this tutorial are derived directly from the SDK examples. The 2 minor changes are the replacement of the wait for start function with a control loop that permits detection to occur even prior to touching the play button on the driver hub. Also, the camera calibration parameters are tuned to a camera that is not defined in the resources of the sample files. The 4 tests are AprilTag for quick detection of all visible tags with customized configuration parameters. AprilTag Easy relies on standard settings for the camera to provide the quick detection of the April tags. AprilTag Optimize Exposure illustrates the effect of exposure and gain on image capture for vision processing. AprilTag Switchable Cameras illustrates the use of 2 cameras either for AprilTag detection or for TensorFlow object detection. The wait for start function is the gatekeeper for continuing processing by the Opmode. Touching the play button permits program execution to continue beyond this function. Since the autonomous period countdown begins when the teams are instructed to touch the play button, it is desirable to perform all housekeeping, initialization, and early detection of objects prior to touching the play button. For this reason, teams often replace the wait for start function with a control loop statement, which is the equivalent of a wait for start check. Within the control loop, code can be executed without time considerations. It is common practice to use the control loop to detect objects, April tags, or TensorFlow object detection images, thereby saving a few seconds from doing the same after the autonomous period. This test is a basic introduction to the detection of April tags. It permits the user to customize settings for 2 key entities, the vision processor and the April tag processor. The Opmode detects all the April tags in the scene and summarizes their pose estimates. It is instructive to use the camera stream to view the scene prior to touching the play button on the driver hub. It is also helpful to assess the field environment for consistent detection of the April tags by moving the April tags slightly and then refreshing the camera view by tapping on the display on the driver hub. Once the play button is pressed, the camera stream will not be available for the remainder of the run. Start with a single April tag and then increase the number of tags incrementally. Owing to the simple nature of the Opmode, too many April tags in the image will make the corresponding pose estimates scroll away. This Opmode makes simplifying assumptions about the camera settings. The same test procedure as in the previous Opmode example should be used to understand the effect of positional changes in the April tags under test. The streaming mode can be controlled on or off by using the D-pad down button on the gamepad. The properties of the camera with respect to exposure and gain can be set in this Opmode. The bumper and trigger buttons on the gamepad increase or decrease the values for exposure and gain. While the original example initializes the value of exposure and gain to minimum values, it is best to use midpoint values as the initial settings. There are 5 interfaces for camera settings: exposure and gain control as illustrated in this tutorial. Also, white balance, focus, and pan, tilt, and zoom (PTZ) can be set for the camera. The latter 3 interfaces may not be supported by all cameras. Also, the use of PTZ settings may inadvertently affect the pose estimates returned by the AprilTag processor. Some cameras permit exposure control settings with aperture or shutter priority, manual or automatic, and continuous. Time permitting, these modes will be explored in future tutorials. This test is a basic introduction to using multiple cameras on the robot. There are many use cases for this feature. 2 cameras used in this Opmode with a single instantiation of the Vision Portal entity process April tags only. The gamepad buttons, as shown on the slide, permit the operator to switch from one camera to the other. The following section steps through the 4 sets of tests with images of test setups and the corresponding display on the driver hub. Before starting the demonstrations of the 4 selected Opmodes, let us view the camera calibration data that are very important for the pose estimates. In the project pane, drill down from team code to res to XML and open the file team webcam calibrations.xml. In this example, in addition to the data for Logitech and Microsoft webcams as supplied by FTC, some entries have been added for the camera in use. Each supported resolution for the camera requires its own calibration data. Notice the structure of the XML. The root element is calibrations, which can have many camera elements, each of which can have many calibration elements, with one for each supported resolution. Specifically, the last calibration entry for the resolution at 640 by 480 has focal length and principal point data from calibration exercises conducted previously. There is a separate video that illustrates the steps to calibrate the camera. The Opmode AprilTag has been adapted from the equivalent concept Opmode under examples in FTC Robot Controller. The structure of the current Opmode is the public class that has one public method and two private methods. There are three fields for internal use by the Opmode. Launch the Opmode onto the control hub and wait for the transfer to be completed. Turn on the driver hub and ensure that you are connected to the correct control hub by noting the names of the network and the configuration settings. Also, quickly check that the battery levels and ping intervals are satisfactory for this simple test. On the driver hub, select the Teleops menu and select the Opmode AprilTag from the drop-down list. Observe the messages on the status pane of the driver hub. If there are no errors to remediate, select the Init button. Then select the three dots on the top right-hand corner of the app window on the driver hub and select Camera Stream from the drop-down list. Check the camera preview window and ensure that an AprilTag has been detected. After each adjustment of the target AprilTag, if necessary, tap the preview window to refresh the image. Select the three dots again and select Camera Stream to disable the preview. Touch the play button to start the detection of the AprilTag. Upon detection of the AprilTag, its Bose estimates are summarized on the status pane. Stop the run by touching the Stop button on the driver hub. Before continuing to the next Opmode, which is a simpler version of the current one, let us make a note of the differences. In the current Opmode, the two processes, Vision Processor and AprilTag Processor, are illustrated with some initial settings that can be changed by the user. In terms of coding style, a basic Java construct is used to change the instantiation of the corresponding objects with the build method. For AprilTag Processor, a few basic settings are shown. The camera lens settings are also applied explicitly. After instantiating the object, camera resolution and monitoring are specified. For Vision Processor, the default stream format YUY2 is generally overridden with MJPEG to consume less bandwidth. After instantiating the object with an AprilTag entity, the build operation can be completed and the processor enabled. In the next Opmode, such detailed steps will not be required since simplifying initial assumptions will be applied. Let us look at the op mode for the next exercise. Drill down from team code to Java and then concept, and let's open up AprilTag easy. If you look at the entities, it's for the class, it's almost the same as the previous one. There are three methods. Only one method is a public, the other two are private, and there are three fields. Again, AprilTag and Vision Portal. So if we move over to the source code, and we can see that the two variables are defined for the AprilTag processor and the Vision Portal. The big change occurs in this construct where we're using the method called easy create with defaults for the AprilTag as well as for the Vision, and thereby simplifying the need to not have any more of those explicit settings. The rest of the code, the telemetry is identical to the previous one, and therefore it should be a very simple exercise to run this. In this op mode, the values for gain and exposure are changed interactively using a gamepad. The left bumper and trigger buttons change the value for exposure, and the right bumper and trigger buttons change the value for gain. Instead of starting with minimum or maximum values for the exposure and gain settings, the op mode was modified to start with middle values for these two parameters. If all the tags in the camera image are detected, then that combination of exposure and gain values are deemed as practical. There are other camera settings beyond the two in this Opmode that may improve the detection of April tags, particularly when motion is involved. These parameters will be explored in a future tutorial. Also of interest is the plotting of a surface map with changes in exposure and gain settings with the number of April tags detected as a color-coded legend. Again, perhaps there will be an opportunity to explore this aspect in a future tutorial. The vision processor supports more than one camera. This Opmode illustrates the use of a gamepad to switch between two cameras. Each camera is enabled by a dedicated gamepad button. In this example, the first camera is activated by the left bumper button and the second camera is activated by the right bumper button. The example permits the use of AprilTag for one camera and TensorFlow object detection for the other. April tags are now officially supported in the FTC SDK. Together with performance and application improvements ensuing from the two key classes, Vision Processor and April Tag Processor, FTC Game Strategy now offers a simpler and quicker ramp up the learning curve for efficient processing of camera images. For the limited purposes of this tutorial, the robot was stationary when the OpModes were run. However, image detection while the robot is moving works satisfactorily too. That's all, folks. Please provide feedback in any which way you can. This presentation was prepared with assistance as noted on the slide. My apologies if I have unintentionally omitted anyone or any resource. A very big thank you to y'all. Come back to the channel soon.